Okay, so first of all, thank you so much to the organizers for this really awesome workshop. Honestly, I love learning things about things I know nothing about, and this is a great workshop for that. I know nothing about cosmology, and now I know epsilon, so I appreciate it. Okay, so I'm really excited to share with you all some very recent work, which is joint with Gage DeZoort. Where's Gage? There he is. He's in the back. So Gage is an amazing PhD student, just literally submitted his thesis. Okay, that's not working. Okay, I'm just going to yell. So Gage literally submitted his thesis today. Okay, so he's about to graduate. It's going to happen. So he'll be a postdoc at Princeton, partly with me and partly in the physics department. So really excited. Okay, so this talk is really at the interface of theoretical and applied deep learning. And it's all about how do you choose architectures and initialization schemes for graph neural networks. Okay, so I encourage you to interrupt with questions if you have them. I like that interactive style, so just kind of yell at me. That's very good. Okay, so I don't know if this thing is going to click. Apparently, we have all kinds of issues.
No, go ahead.
Okay, amazing. Okay, so let me start with just a very brief overview of what the talk is about. I'll define everything very precisely. I'm a mathematician. I can't help myself. Okay, but for the overview, if you don't know what a graph neural network is, just think of it as a popular and flexible method for learning from data that is naturally associated to a graph. Okay, so graph neural networks are great, but like all neural networks, the difficulty in using them, or one of the many difficulties, is the kind of alchemy of hyperparameters. Okay, you have to choose lots of different things to actually get your model to work well. So for instance, you have to choose the architecture. Okay, in any neural network, you have to choose the depth and the width. And as I'll explain in just a couple of slides, graph neural networks have an additional piece, which I call the aggregation operator, sometimes called the message passing operator. Okay, but that's not enough. You also have to figure out how to optimize these things. Okay, Joshua will tell you, you don't have to figure this out anymore. Okay, I'm willing to try, but at least a lot of the time, right? You have to figure out how to initialize your model. You have to select learning rates, which kind of optimizer you're going to use, and so on. And often, unfortunately, a small change in these hyperparameters leads to a big change in performance. So that's kind of painful. And really the purpose of this talk is to try to take some of the guesswork out of making these choices in concert. Okay, so that's what I mean by principles for hyperparameter selection. And okay, in the end, what's the dream principle? I wish I could tell you, just do this and you're going to get state of the art. Okay, that's just too much to hope for, theoretically speaking. So we kind of back off of that a little bit. And what we try to do is we say, look, we don't know if you're going to have a state of the art model, but at the very least, we want your model to start training reasonably quickly. Okay, so I'll make that very precise. But just imagine you would like to at least do epsilon better than random. You want to make sure you don't run into various numerical issues that can plague neural network optimization. Okay, that's the kind of philosophy of the theory we'd like to do, and that'll lead to some principles, which hopefully I can convince you should actually use if you use graph neural networks. Okay, very good. So that's kind of the overview and setting. And because it's a relatively short talk, I figure, okay, this thing is not quite working again, so I'm going to go to this. Okay, oh my God, it works too quickly. Here we go. Okay, this thing is frozen. That's not good. Okay, continue. And so, well, okay, we're going to come back after a brief intermission. Okay, I'm gonna carefully wait here.
Wi-Fi is cutting out.
Do you have any jokes?
So I do have a joke, in fact. Okay, so I was once told, this is what my PhD advisor said, every good talk has 3 ingredients. Okay, it has a joke, a theorem, and a picture. And the key point is that the theorem and the joke have to be different. So that's my joke. Okay, I'm going to get to some theorems, and if the Wi-Fi comes back, there will be some pictures too.
Yeah, Boris.
Yeah.
So on your title slide,
Yeah.
you said ReLU activity.
Yeah.
And every time I have a grad student coming into my office says my network's not training, I just tell them don't do ReLU, do leaky ReLU, and then they're very happy.
Okay. Yes.
And
So
are you
actually,
going to give me anything that will justify?
yeah. So all of this will work for any activation that's homogeneous of degree 1, like leaky ReLU or ReLU or anything like
So you're
that.
not going to help me with explaining.
No, indeed, I'm not. You know, I live to be useless, apparently. Okay. So here's the practical takeaway. Okay, I'm going to show you a bunch of experiments in the course of this talk, and so I just want to spend a minute walking you through what's on the different panels. Okay, so first of all, the left and right columns are 2 standard benchmark tasks that people use to understand how to use graph neural networks. The left one is called Cora. It's basically just a citation data set It's like you have a big graph, you have a bunch of vertices, each vertex is a research article. Okay, and two research articles are connected if they cite one another. And then each vertex has one of 7 labels for the subject of the research article. And your goal is, for a vertex you haven't seen before, try to predict what the general topic of the article is supposed to be. Okay, and on the right, you have a stochastic block model. You have a graph on n vertices called symmetric 2-class stochastic block model. Each vertex is either class 0 or class 1. Okay, those are latent IID variables. And then things of the same class are connected with a higher probability than things with different classes. And your goal is to reconstruct the 2 communities or the 2 classes. Okay, it's just very standard benchmark task. Okay, then there's 2 formulations of these tasks you could imagine. That's the 2 rows. The regression formulation is you just do L2 loss with 1 hot labels, or the classification formulation is cross entropy loss, just predict the labels as usual. Okay, and then the star player in some sense is the y-axis. Okay, this is the number of gradient descent steps you need to take in order to get to the accuracy of the best linear classifier. Okay, I started by telling you the kind of principles I wanted were going to allow you to quickly start training. So our proxy for how quickly do you start training is how quickly do you get to the accuracy of the best linear classifier in your problem. Okay, if you can't get there in finite time, you're going to get fired from your job or not publish your paper or whatever. Okay, so, and then this is basically an ablation study. All these different colors are whether or not you use our principles. And obviously our principles are the red line. Okay, the lower is better, fewer steps. Okay, so I'm going to try to convince you that there's some simple principles. And if you apply them, then at the very least you start training effectively. And if you don't apply them, sometimes you do and sometimes you don't, and you're on your own. Okay, so that's kind of where I'm trying to go. So are there questions or comments at this point? Because I'm about to start defining exactly what a graph neural network is and try to tell you much more precisely what I'm trying to say. Yeah.
Well, what's special about the top right handle that the graph steering over the
I mean, I don't know how to answer that question. So the point is, I don't know how to predict all the details of what will happen on a given task. I'm just trying to show you there's a diversity of things, and the red one is on the bottom. That's pretty much, that's the honest truth. Okay. Yes. Okay. So let me start. Okay, like I said, I'm a mathematician. I got to start with the definition ultimately. So what is a graph neural network? Okay, so a graph neural network takes as inputs signals that live on a graph. Okay, so I start with a graph with vertices v and edges e, and the input is a matrix that I generically denote little x. And to each vertex on the graph, it's going to assign a vector of features. And my notation is that the feature dimension for the inputs is n0. Okay, that's the dimension of the input to the graph neural network that you have. Okay, very good. So then what's the output of a graph neural network? Well, it's almost the same thing. Okay, so I'm about to explain how you get there. But to each vertex in your graph, you're going to try to figure out how to transform the input features to some output features. Okay, and my notation is I have capital L hidden layers, and ZL+1 is like the vector of pre-activations in layer L+1, i.e. the output, and it's just a linear readout in the end of my final hidden layer. That's the L hidden layer. And the only difference is that the dimension's allowed to change. At each vertex, you're allowed to have a feature vector of a different dimension. I call it n sub capital L+1, and in general, n sub L is going to be the width of the Lth layer. Okay, so just like any neural network, the way you go from the input to the output is through a simple sequence of layers. So let me explain how that works. Okay, to do that, I have to tell you what an aggregation operator is, or a message passing operator, or whatever. This is something whose job in life it is to mix signals up among the vertices of a graph. Okay, so formally, for me, I generally call it P. It's a symmetric number of vertices by number of vertices matrix, whose entries are P, U, V. U and V are vertices on the graph. And what you can do is, if you have a scalar signal on the graph, at each vertex you have a number, you can apply your matrix P, and it will mix up the signals among the different vertices. Okay, so on the right is like a common example. This is like a degree normalized adjacency matrix. So the entries of P are 0 unless there's an edge between U and V, but it's not just the adjacency matrix, which would put a 1 there. It's normalized by 1 over square root of the product of the degrees. Okay, people use lots of things in practice, and the theorem I'm about to tell you doesn't care what you use. It's just this matrix needs to be symmetric, and the entries need to be non-negative. That's the basic properties that basically all message passing operators are going to have. Okay, so given such a message passing operator, how do you actually go through the layers of the network? Okay, so I'm going to use my pseudo pointer. Okay, so here you are. You should read this from inside out. You start with the vector of pre-activations in layer little l evaluated at some input to the graph x. So what do? You apply the ReLU or whatever your favorite nonlinearity is component-wise to each of these vectors, right? Then you mix them up by applying the aggregation operator P. And then you have a trainable matrix of weights, which takes you from an n sub l dimensional space to an n sub l plus 1 dimensional space. Okay, that's one layer of your graph neural network, and you just keep going until little l becomes big L. Okay, that's the whole game. So now what I want to tell you about is, okay, how do you choose these aggregation operators? How should you initialize your trainable parameters, the weights? How should all these things play together? Okay, so are there questions or comments about the definition? Because I'm about to start plotting experiments and giving you theorems, but if this isn't clear, it's a total disaster. Okay, it might be a total disaster anyway, but so.
So the output is a graph.
So the output is for every vertex of the graph, a feature vector. And you could use that to do classification of the whole graph or classification of individual vertices or whatever you want. Yeah. Yeah, exactly. Okay, so Show loves abstraction. Very good. That's why one of the many reasons I love Show, right? So if you had a graph with one vertex and no edges, then you get an MLP. That's all it is. So you can think of a graph neural network as strict generalization. Okay.
And the follow-up question would be like, is the principle same? Is it generalization of like creative ID?
Yeah, so exactly. So the main difference is you're gonna have to do some kind of spectral graph theory to understand the properties of your aggregation operator. That's the additional thing you have to put into the analysis. But otherwise, it's very simple. Yeah, that's right. Oh yeah, right. So I should have said that. Thank you very much. So very often in practice, each edge will also have a feature. And those features can be updated. And we choose not to treat that in the theory, although we could almost certainly do it. So it's just a deficiency of what I'm presenting, and you should certainly do that in the real world. Yeah, right.
What is the W? How does it? What's the dimensions of it?
Right. So this thing in here, this is a matrix, which is number of vertices by feature dimension. So this is the thing that you apply per vertex to go from the features in layer L to the features in layer L plus 1, and then you mix things up using the matrix P. Yeah. Thanks. Yeah.
Okay. So is the input just the adjacency matrix, or are the input features something?
No, the input features are whatever they are. They're problem dependent. Sometimes they're nothing, sometimes they're random, and sometimes they're very special, depending on like, the data you have. Well, the edges are encoded by your message passing operator, almost always. It's some function of the adjacency matrix. Yeah. Okay. The short answer is yes, P is going to be fixed throughout the training process, though P could, and as I slyly indicated here, might be layer dependent if you have good principles for graph neural networks. Okay, we'll see. Okay, so here I go. So let me start with principle number 1. How do you initialize such things? Okay, this is one of the original questions I fell in love with neural networks, because I'm a probabilist. And when I realized you could study random neural networks, okay, my life was complete, more or less. Don't tell my wife that, right? Okay, so I'm just rewriting the forward pass, okay, at the top. And what does it mean to initialize a graph neural network? Well, okay, I've for simplicity not included biases, and basically every initialization scheme ever just takes each weight independently from a mean zero distribution. Here I chose a Gaussian, although that's not very important. And so an initialization scheme is just, how do you set the variances of the weights in each layer? That's what it means to figure out how to initialize the network. Now you might ask yourself, does it matter? Maybe I don't care how I initialize this network. Okay, let me show you one experiment, which will hopefully convince you it does, and then I'll tell you how to initialize. Okay, so here's a incredibly kind of simple metric of what your network is doing at initialization. We call it the output distortion. So what do? You look at the size of the vector features at some particular vertex in the inputs relative to the expected size of the vector features in the output. Okay, this expectation is over the randomness in your initialization. Okay, so this output distortion is something that if it's too big or too small is going to impact your training negatively. Okay, and I'll show you that. You don't have to take my word for it. In this experiment, okay, so this is an experiment that we ran on Quora, although we ran this on lots of data sets and we always got kind of similar results. So on the x-axis, you see on the log scale this output distortion. On the y-axis, again, how many gradient descent steps does it take to get to the accuracy of the best linear classifier? So lower is better. And what you should conclude from this plot is that if your output distortion is very small, it's very sad. It just means your outputs are basically 0 to numerical precision or like very, very small. And if it's too big, they're too big, you get a NaN, it's very sad. Okay, so you just want to keep the output distortion somewhere in a reasonable scale. You don't want it to grow or decay exponentially with the network depth. That's the kind of thing you'd like to avoid. Okay, very good. Well, so we have a theorem for that. Okay, the theorem is not too hard, but here it is. So the theorem goes like this. This output distortion is going to grow exponentially in the network depth. So C can be either positive or negative. It might either grow or decay, in fact, unless you tune your initialization to a very particular value for the weight variance. Okay, so the weight variance goes like this. It should be 2 divided by the width of the previous hidden layer times the square of the largest eigenvalue, the spectral radius of your message passing operator. That turns out to be the only value that you should be using. Okay, so let me just make a comment. Without this lambda 1 of P down here, this is a very famous initialization scheme called He initialization or Kaiming initialization, which was originally discovered for ReLU MLPs way back in the day and is used all the time. It's quite important, okay, including that constant too. And what I'm saying is if you just use that as your PyTorch default for using a graph neural network, things are not going to go well for you for deep networks. And the reason is no one said that the top eigenvalue of your aggregation operator is equal to 1 or is close to 1. And so you have to do something that is graph and aggregation operator aware. And I claim this is the right thing to do. And if I have time to get to the last slide and give you a sense of the proof, you'll see exactly why. Okay, so this is principle number 1. Initialize like this and don't worry about it too much. Okay, if you're not exactly at 1, it's okay. You can initialize with a slightly bigger value of CW. Maybe this 2 in some of our experiments was like 2.25. That was pretty good in practice. There's a reason for that, but let me not get into it. Okay, so this is principle number 1. Are there like questions about this? I hope it's kind of clear. Yeah. Well, I wouldn't say it's because I'm looking at the variance.
Ideally, would like to have a order of 1.
Yeah, that's right. So I'm saying you'll get an order 1 number. The output distortion will actually be exactly equal to 1 if you take this at large M. That's what you'll get. That's right. And if not, it'll blow up or decay. Okay, very good. Very good. Let's go. Principle number 2, oversmoothing. Okay, so the previous thing about how to initialize your neural network is, it was specific to graphs, this analysis that we did, but the fact that you don't want extremely big or extremely small network outputs has been known for a long time. So this oversmoothing issue is particular to graph neural networks. It's actually the way I started talking to Gage about this project. So Gage does data analysis at CERN, and he said, hey, we run into various issues that have to do with optimization with graph neural networks, and oversmoothing is one of these issues. Okay, so what the heck is oversmoothing? So let me remind you, here's a forward pass. We initialize the weights in some way. Well, so here's the enemy. Okay, so you have this fixed, for the moment at least, message passing operator P, right? And what do you know happens when you take the same aggregation operator or message passing operator and apply it over and over and over and over again? That's what happens when you go deeper and deeper and deeper in the network. Well, you should probably converge to the top eigenspace of this matrix, right? That's like what power iteration does. And indeed, this is what oversmoothing is. The point is that any of these message passing operators people use in practice, the top eigenspace tends to be either constant or very, very smooth functions on the graph. Okay, so your signal becomes very slowly varying, and it's hard to distinguish anything on the graph. It becomes kind of very featureless. And so that's very sad. And so to make this mathematically precise, let me write pi1 for the projection onto the top eigenspace of your aggregation operator. Okay, and so the point is that to measure how much of your signal is in the top eigenspace, I have to form this ratio. Okay, I call this the oversmoothing ratio. So this is, in the numerator, you take your signal after capital L layer, so this is the final hidden layer, and you project it onto the top eigenspace of your aggregation operator. And you ask, what's the average size of your signal in the top eigenspace relative to the average size of the signal? Okay, so that's like how oversmoothed you are by layer L. And because this tends to converge exponentially to 1, as we'll see pretty soon, I'm going to measure it on the log scale. So I'm actually going to draw a graph for you right now or show you a plot with, on the x-axis, something called the oversmoothing rate. Okay, and this is just something which measures the difference between this oversmoothing ratio and 1 on the log scale. So you can actually resolve some kind of interesting behavior. Okay, as the oversmoothing rate goes to 1, as r goes to 1, this goes off to plus infinity. That's the way it scales. Okay, so what do you see? Well, as you'll come to learn if you ever listen to my talks, I tend to make the same point over and over. You might not even see the difference between the two graphs, but the main difference is that on the x-axis is the oversmoothing rate and not the output distortion. And the point is that for each particular task, here again, we did it for Cora, you don't want too small of oversmoothing because you want your neighbors to be kind of similar, and you don't want too big of oversmoothing because you don't want your neighbors to be too similar. And so there's a kind of Goldilocks zone. You don't want the oversmoothing rate to be too small or too large. Okay, here's, for whatever reason, I want it to be close to 3. I don't know what that really means. Okay, so again, now the question becomes, how do you now choose your aggregation operators? Okay, how do I set up these P's so that I'm not too oversmooth at initialization? Okay, I don't know what's going to happen after 1,000 steps of training. Okay, maybe ask me in 6 months. That's what I tell the funding agencies. But I probably won't know after 6 months either. Okay, that's the truth. But fine. So here I am. Again, I'm just reminding you of the definitions at the top. Here's the oversmoothing rate. Okay, it's the amount of the signal in the top eigenspace relative to the total size of the signal after L hidden layers. Okay, so I have good news and bad news, and I'll start with the bad news. If you use any fixed aggregation operator, as you go deeper and deeper and deeper into the network, oversmoothing is inevitable. Okay, so the oversmoothing rate, RL, is like 1 plus an exponentially small correction. And here really C is positive. Okay, so you're getting very, very close to 1. And it's sad, your networks won't train well. This is like a well-known empirical fact. And so you might say, what's the whole point of this slide? You're just telling me it never works. So why are you thinking about deep graph neural networks? Well, I never said it never works. You just have to be epsilon more clever. So here was our idea. So what we define is, oops, there should be an equal here. Excuse me. So we define these residual aggregation operators, as we call them. And the idea is just to take your aggregation operator that you're using as a base operator, this P, and interpolate it with the identity. This allows you to decouple how much smoothing you're doing in the spectral domain on the graph versus how many forward pass steps you do, how many layers you have in your network. And it turns out that the right units to measure things in are this hyperparameter T. Okay, so the theorem goes like this, that if you use this as your aggregation operator, and notice that the scaling is now depth dependent, then you can exactly control the rate of oversmoothing in the sense that you have bounds above and below. So the rate of oversmoothing is going to be bounded away from 1 by something which is exponential in T. So this gives you like one knob to turn that you can optimize over, which allows you to say, I want this much oversmoothing for this task and this much oversmoothing for this other task. Okay, so in particular, this is independent of L. You can now go as deep as you want and have as little or as much oversmoothing as you want. Maybe this goes back to Shou's comment. If you literally set T equal to 0, then your aggregation operator is just the identity, and no vertices ever talk to each other. So you're never oversmooth. You know, you're always kind of doing fine. Okay, so that's the second takeaway. If you want to use a deep graph neural network, you know, if your depth is basically like 5 or more, you should just use something like a residual aggregation operator. And I should say there are some empirical papers which do something similar together with 17,000 other bells and whistles to get really interesting graph neural networks in various situations. But somehow this is provably a good thing to do. That's the point of this slide. Okay, so let me stop again for a second and ask if there are comments or questions about this takeaway, because this is like the second principle. Use this as your aggregation operator. Yeah.
Maybe I don't. Might be too in the weeds, but I guess if you have like a residual network, typically you have like an identity connection and then you add like a normalized layer output.
Yeah.
And so the fraction of the variance explained by like the identity path is like falls off like a power law in depth. And I guess here it's going to fall off like an exponential in depth because you're like exponentially decaying the path of the layer. Do you think that matters?
So there's two. So I'm about to talk about residual connections in the forward path. So you should think about this as like, how much are you using your neighbors to change your value each time you apply the aggregation operator? So just imagine a network in which all you do is you apply P sub t, and you just do it L times. What you'll roughly get is you'll get e to the t times p. And so because you'll get like the identity plus, you know, t over L times p all raised to the L. That's the kind of thing that you'll have. And so I'm saying this is like a parameter that lets you say how, like, the total strength of the aggregation you're doing across the vertices. Does that make sense? So I'm about to say almost the same thing for the residual connections in the forward pass, but they're actually completely orthogonal to each other.
Yeah, that was super helpful. I'm sorry, I think I was mixing two concepts together.
Yeah, I mean, it took us like plus infinity amount of back and forth to figure out that this is what we should be thinking about. So, yeah. Another question or comment? I forget if
I don't know.
already answered. Okay, wonderful. Okay, so this is principle number 2. Very good. Don't oversmooth too much by using residual connections in the spectral step. Okay, fine. So the last principle, the last kind of failure mode that I want to tell you about is, again, something that people have known about for quite a while. So this is the least interesting part of the theory in the sense that this theory was essentially already done for us in prior work. So I'm just reminding you of the basic forward pass equations at the top. So, but still, we call it correlation collapse. And so we're going to define a single number, which I think you should care about in these graph neural networks, or really probably in any classification task. So it goes like this. You fix an input x to the network, and then you look at the final hidden layer. So z capital L of x is just these activations at each vertex in the final layer. And you just fix a class. So you have a classification task that I have in mind here. You look at all the vertices that are supposed to be classified as class C, and you just average their feature vectors. Okay, so you form a matrix, which is number of classes by number of dimensions in your final hidden layer. It's just the class averaged features. If you know about neural collapse, this is the kind of thing that collapses. Okay, and kappa for me just literally means condition number of this matrix. Okay, so I claim that this condition number is important because it measures just how diverse are features across different classes at initialization. You know, if in the worst extreme, every vector that you have as an input gets mapped to the same output. Every vertex gets the same random feature vector. You'll never be able to distinguish anything. Okay, so don't take my word for it. Take Gage's word for it. Okay, so same y-axis, different x-axis as usual. Here you plot the class condition number. Lots of different networks, different depths, different learning rates. And the point is, you don't want the class condition number to be too small, and you don't want the class condition number to be too big. Again, you just want it to be some kind of reasonable order 1 number. And what I want to say in this, again, is the content of prior work. So I write it as a theorem, but it's kind of just a trivial observation based on what people already knew. If you now have residual connections in your network, and at least you can always scale them this way. So maybe the only interesting part of what I'm saying is I'm proposing a particular way to parameterize the strength of the residual connection. So there's a hyperparameter beta, and it's divided by L, and you take a square root. So beta is like the effective strength of your residual branch. So it turns out if you have a moderate value for beta, this will provably allow you to have a moderate value for the class condition. Okay, so that's kind of principle number 3. You should think about using residual connections in the forward pass part of the network. But if you're going to go really deep, okay, we didn't put layer norm in here, so you have to normalize somehow. And these constants here help to modulate the effect that each residual branch is going to give you. And that's like Josh's point. You don't want like the residual things to blow up either. Okay, so those are my 3 principles that we sort of like, after a lot of late nights of thinking about it, came up with Gage. Okay, so initialization, you should initialize with this kind of like generalization of Chi-Ming initialization. That's kind of the only thing that will allow you to avoid exploding or decaying kind of outputs. Okay, because these models are homogeneous of degree 1, that also will give you like exploding or vanishing gradients if you don't do this. Then in the forward pass, you should use residual connections because residual connections are your friend and they allow you to propagate correlations in the input and not forget them in deep networks. And you should use residual aggregation operators, and you should have these 2 new hyperparameters, t and beta. And the truth is, we don't know how to set them. We had some kind of version of this discussion earlier today. You need to set them by tuning them for your particular task. I don't know. That's, I think, the best we ever came up with. Does that sound right, Gage? Yeah. So again, you know, that's going to be data set dependent. That was your question, Jesse. I remember. So for me, t and beta, but like this is the right parameterization. Okay, and we don't do learning rates yet. Okay, we're not sure how to do it. Okay, so this is the practical summary. Initialize right, use the residual P and the residual connection, and at least your network will be trainable at the beginning. Okay, I make no promises about how well you're going to do after training. Okay, so yeah.
Like for condition, second one, like probably setting it as a MLP setting.
Yeah, exactly. So the first condition, we have to figure out how to generalize the MLP setting to know about the spectrum of the aggregation operator. That's the thing that wasn't completely clear before. The second thing, I tried to say it a couple times, this is literally what people will tell you to do at least sometimes in the MLP setting. That's like a way to scale the residual branches and get some kind of order one signal at large depth. And then, okay, this thing, again, like we didn't see anyone ever analyze this. This is sometimes used in practical papers or some version of this is used. And we're just pointing out this is a good thing to do. And there's some more or less transparent way of thinking about why it's a good thing. Yeah.
What stops you for generalizing this to other application functions?
I'm about to get to that. So yeah, so Show's question is great because it's gonna lead me to the next slide. But let me just say again, like all this analysis has a downside, which is it's only for ReLU or leaky ReLU or anything that's homogeneous of degree 1. But it has an upside, which is none of it is infinite width. This is all literally at finite width. They never took n to infinity. It's like you don't have to worry about any of that. So let me explain why that is. But like in a nutshell, it's because the ReLU actually plays really well with these kind of aggregation operators in a way that other nonlinearities don't, or at least don't obviously. Yeah.
So, we got the first condition just by looking at the forward pass, right? Like
Yes.
Analog of energy beacon.
Yes.
Yeah. Is there a way to analyze also the backward pass that gives us, like, does it give us the same condition, or does it give us a condition on the learning rate? Or
So the short answer is it will give you conditions on the learning rate, and you can use the meta principled strategies, or you could use the ABC parameterization to set those. And we just don't try that. Like we didn't do it in the paper, but there's nothing stopping you at all, except maybe not enough coffee or something like that. Yeah.
So the beta and the T skip is designed to make choices.
Yes.
Let's just say the last one, aggregation.
Yeah.
If I didn't have to choose the T, would it be just as valid to do a concatenation of the identity and whatever it might be? Is basically just have my dimension of my output space just be, I guess, twice as big, where I have an identity going to one block and then the P going to the other block and going from there. Like, do I have to do does that
Yeah,
plus have to be a plus, or can it just be a circle
that's
plus?
an interesting question, and I suspect you could do something like that. I'm not sure, but then again, it'll be a question of what's the relative initialization scale of the weights that go between the different pieces and the weights that go, inside the pieces. And I think there will be an effective T that you're going to get out some. Because you're going to ultimately ask how much of the identity do you want to use and how much of P do you want to use, and you'll always find that things will be exponential in the P, so you better use only one minus. That's my guess, but there are many things you could try, and we certainly didn't try all of them.
Let me ask that question a different way. Can T be a learnable parameter? Trainable parameter. Yeah.
Well, I don't think we ever tried that, but you can literally make T a trainable parameter. Everything is perfectly differentiable.
But will T go to the right value, or will like a nice value, or will it also run off in a way that
I don't know. Yeah, I don't know. That's a great question.
I'm worried about thinking.
Well, just set T equals to 1. I mean, in the sense that at the very least, if you set T equal to 1, even if your depth is 20, your thing's just going to be fine. It might not be the best for your task, but you're not going to not be able to start. That's kind of the point. Like because you're choosing T on the right order 1 kind of set of units. Yeah. Maybe Gage will strongly disagree because of course he did most of the optimization for the hyperparameters. But I think we found it was fairly robust for starting the train.
So you have 10 minutes left for your questions now, but you've been taking questions as you.
Okay, great.
So wrapping up in the next.
Okay,
10 minutes.
perfect. I will do that. I will be either that or early.
Okay.
What's that? Oh, yes.
To keep this top eigenvalue unique for real, you have like a convenience type description of the P.
Yeah, so I probably said it too quickly. Indeed. So P is symmetric, and all of the entries are non-negative. So it's exactly, so that's going to be the starting point for the next slide. You have to apply the Perrin-Frobenius theorem, and otherwise I don't know what to do. Yeah, correct. I mean, Okay, very good. So indeed, let me give you at least a glimpse of the proof. Okay, there's only like 4 bullets in this slide. So the first bullet was already conveniently reminded us. Okay, so this is not our theorem, it's the Perrin-Frobenius theorem, but I'll remind you of it. So if you have any symmetric P, then if it has non-negative entries, there exists a basis for the top eigenspace of P. This is basically the like eigenvectors that tell you the stationary distributions that your Markov chain can have when you start running P over and over, with the special property that each entry of each basis element is greater than or equal to 0. Okay, that's like that's what the Perrin-Frobenius theorem tells you, or at least this is one equivalent version of it. Okay, so the point is that there's just a basis for this top eigenspace, which is the enemy in oversmoothing, where each component is greater than or equal to 0. And what do we know about ReLU? Well, the ReLU plays particularly well with non-negative entries, right? In fact, it's just the identity on things that are greater than or equal to 0. So if you form the projector onto this eigenspace, literally the sum of pi j transpose, every entry of that projector is non-negative. So it commutes with ReLU. That's sort of the beauty of it. Okay, so ReLU commutes with the eigenspace projection. This allows you to basically interchange, at least in the top eigenspace, the action of the ReLU and the action of your aggregation operator. And that, of course, makes things way easier. Okay, so the second thing, and this is in some sense the most technical of the calculations we have to do. So I just told you that the top eigenspace for your aggregation operator is invariant under your nonlinearity. And the thing you have to check is that every other eigenspace maps at least a little bit to your top eigenspace under the action of ReLU. It's not totally crazy because ReLU makes things positive, but you have to check that. Okay, so this right away tells you that as you go deeper and deeper in the network, signal is going to accumulate more and more and more in the top eigenspace of your aggregation operator, and that's why you're going to be oversmooth. Okay, and at large L, the point is that P will just act like the identity times the top eigenvalue of P, because almost all your signal is going to be in the top eigenspace of your aggregation operator. And this tells you right away that you have to rescale the standard deviation of the weights by 1 over lambda 1 of P. In other words, you have to rescale the variance by 1 over lambda 1 squared. Okay, that's essentially how the theorem is proved. And then once you have that, this is like the key to the analysis, and this is why we needed to do ReLU. Okay, so like other things that are positively homogeneous will work fine, but tanh won't work that well unless you go to infinite width. And then it's close to being linear. You know, you get the 1 over L for the kernel, and you can apply this. But we chose not to take that route. Yeah. Right. Okay. Other questions or comments about the proof? So I actually lied to you. My advisor actually said there were 4 things you're supposed to do in a talk. You're also supposed to give a proof. Okay. But I didn't want to say that at the start because I wasn't sure I'd have time to get to it. So, but now that I've gotten to it, I feel okay. And he'll be happy. He'll be happy to know that I made it all okay. Okay, I think we should just stop. This is exactly 5 o'clock, which is I think when we were supposed to end. So I'm happy to take questions or discussion either right after or just offline.
Any questions? We can take a couple. Realizing it's 5 o'clock, people can leave.
So for P that's reduced in scans where you do the symmetric renormalization.
Yes.
Yes, for example, if your graph was uniform, that would restrict the top eigenvalue to around 1.
Yes.
For generic graphs, I would expect it to still also kind of cover around 1.
Yes.
So does that mean it automatically satisfies? Would mean that you don't worry too much about that?
Yeah. Okay. So I should have said that and I forgot. So it's a great point. So part of the issue is that if each input to your network is a graph, P could have very different top eigenvalues, and that's kind of weird. And indeed, a common thing people have found is good in practice is to do degree normalized. Often you add some self loops to it to regularize it kind of further, adjacency matrices. And like our partial explanation for why that works is that indeed, that's an automatic way of setting lambda 1 of P equal to 1. And so you know, that's a good thing to do and should always be normalizing in a way that does that appropriately. That's kind of like a like post hoc way of explaining something that people do in practice, though maybe not always.
Any other questions?
So does the top eigenvalue appear in most distributions for the initialization? For example, you chose the normal here and the lambda one came up.
Yes, got it. So the truth is all the stuff we did had nothing to do with the Gaussian. You just had to be mean zero. You had to be symmetric around the origin, have the variance that you were trying to set. We only ever did second moment calculations. If you saw in all the objects, there's expectations of squares, but never higher order things. The higher order things are interesting, but they're more painful, so we avoided them. That's the truth. Yeah.
Let's thank our speaker again.